old is 20.
It's 4 years.
18?
Yeah, so
4 years.
4 years.
Hour and a half. We actually got it for graduation. So it's 20.
How about here's
I got it this one.
here's my dilemma.
You gotta come up with your other.
It's been a while since I've been communicating.
Because you said, look,
With
give
a
me.
woman in
It's like, okay, then you try and do something that's perfect.
I've actually never had to deal with that. 'Cause I've never like used the example.
My heart.
Like,
Living like things.
was that?
You should call Maverick.
Honestly, yeah. I heard that or fact that,
Yeah, it actually fits.
Bro, I'm definitely liking that.
Really?
That's a cool name.
That's a baller name.
That's fair enough. I'm gonna my kid a Chumbias by something.
We'll say.
No.
If you name your kid to stay, I'm beating you.
You will see. No, I'm naming him Mateo.
Mateo? Oh, that's pretty good.
Yeah, right? And it's not that massive shit either. It's Mateo or Mateo.
Either that or big, no, Victor sounds really weird.
Victor is like a weird name that can actually like go both.
Learning objectives.
Oh, wow. Like if you name your daughter Victor, you're like, oh, Victoria.
That's where my middle name came from.
Or like, you know, you can name her Meg, but people don't know how to short for Megatron.
Yeah, true.
True.
Good parent. Gotta respect it.
Either that or Megatron.
Or Megatron.
Megatron. Bro, look at you really go pilot.
That, you like that one, bro?
I
That's
hate,
literally like
I
this.
hate you.
Yes.
That was the one that Caesar was the.
Yeah,
What is it?
What's that poster?
it's a glove because I think my sweaty ass palms keep rubbing across my my iPad screen, so it keeps making the pen go crazy. So
Oh, is that what that is?
So right now we're gonna.
we'll find out. You'll be the first to see. Wow, it literally just covers your pinky in here.
Dr. Weiss had her applicants with like functional a lot.
Oh, really?
I think that was her like, that was like her off-brand one though.
No. But even the Gen 1 applicants, so this is like her third one.
Oh, really?
Yeah, it keeps like.
I imagine.
Wow.
Yours do
It's really weird.
Yeah,
She is actually the Tim.
Mine doesn't do it. Well, I'm still. How, or my tablet does hold me hostage.
Are you sure? Are you sure?
Yeah, go for it. I don't think I've said it.
Okay.
What's it? Huh? What's it? Your money now. I just made you. Say it out loud. NRG. Like. Gaming board? No, energy.
Oh.
Oh, that would know that. NRG. I've never seen anything. Energy is too long of a word to spell, so I made it, so I shortened it. Oh my God, you know. Bro, you should have mentioned having your stoves. Like he said, his mask. Oh, sir. Thank you, sir. Your genius, I appreciate it. What? What? Oh, dude, I can give you a lot of the bullshit. I do.
Why she is that?
Yeah. Oh, she's a city. Yeah, that's like what. Yeah, static. Yeah, I can do this. Okay. You.
No, I say, enjoy the class.
Me?
We have a.
This video. This is the direct to
Over.
Yeah, we have
I think I started now. maybe like their Stokes. Measured dose. Assuming like ideal conditions. If you lost it.
I mean, I just need to follow it, you know. I have it right. It's bad working with so many things.
Yeah, I mean, they're called technically.
If you guys haven't had a chance to pick up your exam yet, you guys can pick it up, because, you know, I gave it out on Monday.
I just know.
Right?
Go over.
Yeah, of course, definitely.
My friend tried it like
Too far, too low, too young.
Yeah, I thought so.
Where's that? Most of it's probably.
My friend tried semester in like 4 weeks, got nothing, got a present on the stove. And that's what happened.
For me, it's really boring.
Oh, yes.
Yeah.
But like, you know.
Yeah.
Really, really well.
Yeah, this guy's
I'll take a spin, I guess.
I wouldn't go like that.
I mean, yeah. That's what I was
To define
trying.
radiosity.
Where?
Radiosity.
I guess it's a thing.
I don't know if that's how you pronounce it.
It is.
Cool. Thank you. I've never. Or is it radiosity? Radiosity. Radiosity. No, I'll give this. No, send her.
You guys. Of course you will with that attitude. You gotta believe you can do it first. Well, I mean, it starts with belief, right? You gotta believe you can at least do well.
That was my mindset coming today.
Uh-huh.
Good afternoon.
I think you're fine.
I don't remember. One time I got out of the festival. I did mine a little bit.
You know, I think there's so many rules people attend because the next class is the. No, it's the.
All right, it's 2:30, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Tired, yeah. Yeah, sleep 15. Yeah, it's, I'm tired too. We're all tired, but you know, we're almost there, almost there. Okay, so the plan for today is we're going to continue on with our lecture notes on radiation. Okay, and so last time we went over this idea of radiation exchange, and today we're actually going to be doing some problems to see how that actually applies in practical situations, right? So I'm going to lead off with actually an example today, and so it's one that we didn't get to last time, but hopefully, you know, you'll start to see a lot of these concepts in action. All right, and so with that said, you know, I think, you know, just kind of judging just based on how much information we have left, I think we should be able to finish by after Monday's lecture. And so I want to spend next Wednesday's lecture reviewing for the final. And so what I plan to do, probably not today because I need to finish grading an exam before lecture today. Not New Year's, but another lecture today. But probably by tomorrow evening or Friday morning, the latest, I'm going to post the study guide for the final exam. The glove is not helping. Maybe. Yeah. Okay, and so the study guide for the final exam should work in basically the same ways as before. And so, you know, it'll have all the topics, all of the learning objectives that you'll be responsible for. And the final exam is going to be cumulative. And so, you know, I know we're covering some new stuff with radiation, but that's not enough to cover a full exam. Okay, and so we're going to have to, you know, we're going to be factoring things in from conduction and convection as well. Okay. It's going to be cumulative, but it's not going to cover absolutely everything. And so, you know, we've been at this for, you know, by next week we'll have about 15 weeks of content. And so, you know, I'm not going to expect you to know 15 weeks worth of content for just one exam. And so I am going to trim the list. I'm not going to, you know, I'm not going to say, you know, we're going to cut out conduction or convection, but within those topics, within those units, I'm going to cut out certain weeks. Okay. And so in total, it's probably going to be around maybe 70 to 75% of the content we've learned this semester. Okay? All right, the glove's not helping. I'm going to take off the glove. We still have $5 on that thing. Okay. And so you can probably expect to cut out some of the more niche topics. So something like fins, I think transient conduction also, you know, I'll probably cut that one out as well. We'll probably leave off free convection as well. And so, you know, some of the more niche stuff, you know, I'm hoping that I can probably cut the list down to maybe like 11, 12 weeks worth of content. You know, maybe closer to 11 weeks of content for you guys to study for the final exam. Okay. And so it is going to cover stuff all the way up until the first week, but you know, it's not going to be every single week up until then. Okay. So I haven't made my final decisions yet. I haven't written the final exam yet either, but you know, by tomorrow or Friday morning, the latest, then you'll have that list. Okay. And just like I've done for the previous exams, you know, once I put the study guide out there, I'm going to post a poll on Canvas as well, so you guys can vote on what topics you want me to cover in the review session on Wednesday. Okay, and then we'll spend Wednesday's lecture reviewing for that exam. All right. And so, are there any questions I can answer before we get started today? Okay. All right. So we'll talk more about format for the final exam later. But you know, what I'm thinking is that you guys can bring 2 cheat sheets for the final exam, just because the final exam just is naturally going to be longer. It's going to cover more content, and so you know you're going to need more cheat sheet space for that. Okay, but we'll talk times and everything next week. Okay. All right, and so to kind of recap where we were last time, I want to scroll up a little bit in these notes. Okay. And we went over this idea of radiation exchange, right? And so what we said is that you know, when 2 surfaces are different temperatures and they can see each other, then they're going to exchange heat by radiation. Okay. And so the term radiation exchange is now I'm kind of realizing now it's not the best name because the heat's only going one direction, right? It's not that, the overall heat's all going one direction, but it's not that they're really kind of exchanging heat, okay? And so these two quantities here, right? So remember, we have two expressions for it. Both of these are expressions for how one surface can transfer heat to another via radiation, okay? Okay. And so the key quantity in all this, besides the temperatures, of course, temperatures are always going to be most important, are these two quantities right here, okay? And so we spent a good amount of time talking about them last time. And remember this Fij or Fji, these are the view factors. Okay. And what the view factors represent is how much one surface can see another one, okay? That's essentially what they mean. And so a lot of these radiation exchange problems, what they really boil down to is how can we determine these view factors? Okay? And so that's really going to be the key. And last time we spent a lot of time talking about, how we can do that. So we talked about the 3 rules, right? So we talked about the reciprocal rule, we talked about the completeness rule, as well as inspection. And so that's kind of like the third rule. But sometimes you're going to have to rely on tables when all else fails. Okay, and so this next example here is going to show you a situation just like that. Okay. All right, so that's just a recap of what we did on Monday. Are there any questions on this? Okay, right. So let's do an example here. Okay, so let's say that we have a rectangular furnace. Okay. And so the furnace is going to look like this. We're going to have one wall. It's going to be another wall. And the third wall, like that. Okay. We'll call this surface 1 right here on the right. The bottom surface will be surface 2. We'll call the left wall surface 3. Okay. And this furnace is technically open, right? And so the fourth wall is left intentionally open. But remember last time, in order for us to form our completeness rule, we can go ahead and draw kind of an imaginary surface here as well. Okay. And so I'll call this you can call it surface 4, but because this is kind of an open surface here, I'll call it surface infinity. Okay. And so someone was asking about, what this kind of imaginary surface represents, right? And so because this surface is open, what we say is that any radiation that passes through the infinity surface, we'll say it's radiation lost to the environment or lost to the surroundings. Okay. Okay. All right, so let's put some temperatures on this guy. So let's say that T1, okay, so that the temperature of the right wall, this is going to be 1,000 Kelvin. Okay, so it's super hot. Okay. T2 here is going to be 800 Kelvin. Okay. And T3 will be 600 Kelvin. Okay. And then T infinity, or the temperature of the surroundings, will be about room temperature. And let's say it's about 300 Kelvin. Okay. All right, so let's put some geometric dimensions here. And so let's say that the length of this wall right here, this is going to be 0.5 meters. Okay. The length of the of surface 2 and by extension surface infinity as well is going to be 0.1. Okay. This surface is identical, so we say 0.5 as well. Okay. And so what we're going to say also is that the depth of this geometry into the page will be 1 meter, just for the sake of simplicity. Okay. Okay, and so from this example, what we're interested in computing is we want to compute the radiation exchange between surface 1 and surface 2. Bless you. Okay. 2, let's compute the radiation exchange between surfaces 1 and 3. Okay. And 3, let's compute the radiation heat loss between from surface 1 to the surroundings. Okay. Okay. All right, so there's a lot that we can compute here, but we want to focus just on surface 1 just to kind of make things a little bit easier. All right, so that's the setup for the problem. And so are there any questions on this? Okay. All right, so since we're concerned with radiation exchange, of course, we're going to be using this formula up here, right? And so what we can say is that Q exchange is going to be equal to, let's copy the formula down here. So we have Fij Aj or Ai, excuse me, times sigma Ti to the 4th minus Tj to the 4th. Okay. Okay, so let's look and see what we're given in the problem. And so, you know, we have all the temperatures, right? And so all the temperatures in this problem are given, and so we don't have to worry about that. Okay. Sigma is our Boltzmann constant, Stefan Boltzmann constant, and so that's also going to be known because that's not going to change. Okay. Right. We also can compute all the areas, right? Because we know all the geometric dimensions, and so we know the length as well as the depth of these surfaces. Okay. And so the only thing that we don't know here are the view factors. Okay? And so a lot of this problem is going to be focused on how do we compute those view factors and then plugging it into the problem. Okay. Okay. And so let's start with radiation exchange between 1 and 2. Okay. And so radiation exchange between 1 and 2, so we'll call this Q12 will be, right? So since this is between 1 and 2, the view factor that we want is F12, okay, times A1 times sigma times T1 to the 4th minus T2 to the 4th. And of course, you know, what we need to find here is F12. Okay. All right, so let's go through all of our rules here to see, you know, if we can compute F12 from anything in this picture. Okay. Okay. So this situation is a bit more complex than the one we did last time, right? So we have 4 surfaces here. Okay. We have an enclosure, which is great, and so we can use our completeness rule. Okay. And so what we can say is that by completeness, okay, by completeness, if we take F11 plus F12 plus F13 plus F1 infinity, right? We add those all up, it's going to be equal to 1. Right? Okay. And so we have 4 unknowns here. And so, you know, we have, you know, not enough information to solve this, but we can cross one of these out, right? And so right away, we can say that this is equal to 0, okay? Because remember, F11 is the view factor of the surface with itself. And we can only have those cases when our surface is convex, right? Or excuse me, concave, okay? And so since our surface here is flat, then there's no way for surface 1 to radiate on itself without bouncing off something else first, okay? So you have 0, surface, flat. Okay. All right, so that eliminates one of them, you know, but it doesn't really help us here because we have 3 more unknowns. Okay. So let's try the reciprocal rule. Okay. And so by reciprocal rule, we know that F12 A1 is equal to F21 A2. And so we look and see, does this help us? And so, you know, we know A1 and we know A2, right? So that's good. But we're still kind of stuck because, you know, we don't know F12, that's the one we need, but we also don't know F21 either, right? Because it's not really given to us in the problem. So this is also not that helpful to us. And in fact, for this problem, it's actually going to be useless to us. We're never going to come back here. Okay? Right, and so the last rule that we have, of course, is inspection. Okay, and so if we look, can we see if there's anything obvious in this geometry here that allows us to kind of solve for one of the view factors outright, right? And so we have these two plates, or 3 plates, excuse me. Okay, and so we can see from this geometry here that there's nothing really too obvious because, you know, some radiation is going to come off the surface, it's going to go here, some of it's going to go here, some of it, of course, is going to go out to the surroundings, right? And it's all going to go in different directions. And so inspection here doesn't really help us out either as well, because, you know, we don't really have an obvious solution. Okay. Okay. And so we're kind of stuck, right? And so none of our rules here were really useful to us. And so where we can go from here is we can use a table, okay? And of course, you know, you don't have to go through this entire kind of process here that I went through. But I do want you guys to check these rules first, because, you know, sometimes you'll be surprised sometimes that, you know, if you use one of these rules, you know, you might find something that you want before you have to go into the table. And so the table, right? And in this case, because it's a 2D situation, we're going to look at table 13.1. Okay. This just so happens to have the exact geometry that we need, partially because this is an example from the book. And so, of course, they're going to have the exact geometry. Okay. But I want you to save the table for last because, you know, tables can be useful. And so if you remember when we did 2D conduction, you know, we looked at tables for shape factors then. So tables are useful when your situation can match up exactly to what's in the table, but reality usually is not that nice, right? And so reality is usually a lot more complicated than that. And so you're not going to find a table entry that exactly matches your situation. And so, you know, so that's why I said, you know, try to use the other rules first if you can. As a last result, you can look as a last resort, you can look at the table. Okay. All right, and so if you look in that table, I'm not going to reproduce it here, but you'll see that there's a situation here that that matches our geometry exactly. Okay, and so that situation is perpendicular plates with a common edge. So that's the name of the entry. Sounds like a modern art exhibit. And so if you look at the figure in the table, it looks something like this, right? And so we have two plates like this, okay? Right? And so of course we're seeing a 2D view, and so we're not seeing the whole length, right? And so this is dot right here that I drew, this is the edge that they share. And so the key for this table entry is that they have to have an edge that's, you know, that's common between them. Okay? All right, and so if you have a situation like this, then there is a formula out there for the view factor, okay? And so what we can say is that F12 here is 1 plus L2 divided by L1 minus 1 plus L2 divided by L1 squared. And all this is square rooted, raised to the 1/2. And all this is divided by 2. Where this is L1, I believe. Yeah, this is L1, and this right here is L2, okay? And so it just so happens to match up with our example exactly, right? And so we can go ahead and plug in the length here, okay? And so if we plug in, L2 here 0.1 meters, and L1 is equal to 0.5 meters. Okay, so these came from the problem. Then if we plug those in, then what we get is F12 is equal to 0.09. All right. And so now that we know F12, we have everything that we need for this equation right here, right? So let's go ahead and compute that. And so we can compute Q12 is equal to F12 here, which is 0.09. Okay. We have the area. The area of the plate is 1 meter multiplied by 0.5 meters, okay? Because this is the area of plate 1, okay? And we multiply by sigma, and so sigma here is 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the 4th, okay? And we multiply by the temperatures. And so the temperature T1 is 1,000 Kelvin raised to the 4th power, and the temperature of surface 2 is 800 Kelvin raised to the 4th power, okay? And so we plug all those in, we punch into a calculator, and what we get is 1506 watts. Okay. Right, so that's part one of the problem. And so, you know, in this part, you know, we had to rely on a table to compute our view factor. But once we had the view factor, it was just kind of plugging into our radiation exchange formula. Any questions on this? Okay. All right, so I know the next part of the problem asks the heat transfer between 1 and 3, but I'm gonna go ahead and skip that for now, because what we can see is that if we look at the geometry here, right? We look at surface infinity, you know, this is an identical situation to surface 2, right? And so I'm gonna go ahead and skip to part 3 for a second, because that's gonna be identical. Okay. So 3, heat loss to surroundings. Okay. And so this is also, you know, a perpendicular plates with a common edge. right? And in fact, it actually has the exact same geometrical lengths as well, right? And so one length is 0.5 meters because that's still surface one, and surface infinity here is 0.1 lengths or 0.1 meters in length as well. Okay, and so due to symmetry, or I guess you can classify this as inspection as well, right? So that's something you can observe. Okay, it doesn't really matter what you call it. Because the geometries are identical, we can say that F1 infinity is going to be the same as F12, which is going to be 0.09. Okay. And so now that we know the view factor for surface infinity, we can go ahead and plug that into our equation here. Okay, and so we can say that Q1 infinity is equal to F1 infinity A1 sigma. Right. We're not going to have the same heat transfer though, because the surroundings are at a different temperature, right? And so this can be T1 to the fourth minus T infinity to the fourth. Okay. Right, where T infinity here, remember, is 300 Kelvin. Okay, so even though the geometry is the same, don't get kind of suckered into skipping too many steps because the temperatures are often going to be different. Okay. All right, and so if we plug in everything from this expression here, what we get is 253083 watts. Okay. And so we have a significantly higher amount of heat transfer here. Okay. Because the temperature difference is a lot higher. Okay. And so surface two, surface infinity are the same, but surface three here is different. Okay. And so surface three here is not a perpendicular plate, but it's a plate that's kind of separating the two. Okay. And in fact, we can characterize this as, we can say that these are parallel plates separated by a midline. Okay. And so the reason I call it that is that this is actually in the table as well. Right? And so if we can draw our two surfaces here. Okay. And so we call the length that separates them L3. This is L1. This is L2. Okay. There's a formula for this in the table as well. Okay. So this is also in table 13.1. Okay. And from that table, we can say that F13 is equal to W1 plus W3. Question in the chat, so why don't we do F13 is equal to 1 minus F12 minus F14? You can do that, and so you can definitely do that. And actually, that would be the preferred way. But I want to show you that you actually arrive at the same answer from both ways. Yeah. Because taking this from the table actually takes longer because these formulas are seldom simple, and so they're usually pretty complicated. Doesn't help that my Apple Pencil has a mind of its own right now. Okay. All right, so W1 and W3 here, I should call them W. Yeah, that's fine. W1 and W3, so you're probably wondering what those are, because I didn't draw those in the geometry, right? W1 and W3 here are actually ratios of the lengths, right? So W1 here is going to be L1 divided by L3, and W3 here is going to be L2 divided by L3. I think it should be W2, but I have a typo in that. But anyway, the point is, I wanted to show you this formula to show that you can use it, but sometimes they're a bit more trouble than it's worth, because these formulas are pretty long, and of course you're punching this in the calculator. Especially you're doing this on the exam, you're going at like 300 miles an hour, and it's really easy to make a mistake here. Okay, but if you do end up plugging in all the values for this, what we can say is that the view factor between surfaces 1 and 3, the parallel plates, is 0.82. Okay, and you get that from this formula here. Right? But as Keith mentioned, we've already solved for F12 and F1 infinity, right, and F11 as well. And so another way, or what I think is the much easier way to solve this, is to use completeness. And so if you remember from completeness, we can say that 1 is equal to F11 plus F12 plus F13 plus F1 infinity. Okay. We know F11 is equal to 0. Okay. And we've already solved for F12, F1 infinity. These are both 0.09 and 0.09. Okay. And so that just leaves one unknown in this equation. Right? And so if we solve that for that one unknown, we get F13 is equal to 1 minus 0.09 minus 0.09, which, by the magic of math, is also 0.82. Okay? Right. So actually, I'll let you guys be the judge. And so, whichever you guys find easier, if you want to look up these things in the table, you're going to get the same thing. Granted, the geometries are matching the same way, but if you can use one of the other rules, our reciprocal rule, our completeness rule, or inspection, right? If you can use one of those things, those are usually going to be a little bit easier, at least in my opinion. Okay. All right. So either way that you compute F13, we have everything that we need, and so now we can compute Q13. Okay. And so Q13 is going to be F13 A1 sigma T1 to the 4th minus T3 to the 4th. Okay. We have a much higher view factor here, and our T3 here is fairly low, well, low compared to surface 1. And so what we get from this is 20,234 watts. All right. So that's a good example. And so, with this example, we've kind of seen, how all this kind of connects together, right? And so the key that you'll see in these radiation problems is finding those view factors. Right? Once you can find those view factors, then you're going to be in good shape for these problems, because it's really just a matter of plugging into just one equation. Okay. In some sense, radiation is pretty different from convection. And so in convection, you guys just experienced it. There are a bajillion different equations. But for radiation, there's only a few, and this one right here is probably one of the most important to know. Okay? And a lot of problems are just built off this formula here, but just with different geometries. Okay. All right. Any questions on this example before we move on? Okay. All right. And so that example there, I think, was a good example of radiation exchange. But those were for perfect surfaces. Okay. So we say this example assumed This example would assume that all the surfaces were black bodies, right? And so that means that epsilon is equal to 1, right? That's the emissivity. The absorption is also equal to 1, okay? And we also assume, kind of more importantly, that there's no reflection and also no transmission, okay? Okay. And so that's fine up to this point. And so, you know, we're still kind of getting the hang of radiation, but of course, real surfaces aren't really like this, right? And so, you know, we want to be able to extend this analysis or these tools to account for those real surfaces. So you can actually do this, you know, you can actually use this in practice, okay? And we're going to be doing it only in really kind of just one specific situation, which I call gray body radiation exchange. Okay. In particular, you know, with gray body radiation exchange, you know, we're going to lift our assumptions a little bit. And so we're going to now account for situations where the emissivity is less than 1. Okay. Okay. And so our surfaces are not going to be perfect emitters anymore. Okay. And more importantly, we're going to consider situations when we can have radiation reflection as well. Okay. Okay. But we will hang on to kind of one key assumption, right? And so that's the assumption of a gray body. And so if you remember on Monday, we talked about this. Okay. And so what the gray body assumption basically states is that the emissivity and the absorptivity, they're still going to be the same. Okay? All right. So this changes things up quite a bit because, you know, now that we're considering reflection, you know, what we can say is that there are multiple mechanisms for radiation to come off of a surface. Okay. Okay. Because before what we said, right? So we had our, you know, our radiation potato here, right? So what we said is that, you know, when this potato here is emitting radiation, right? Then all the radiation that comes off of it is due to emission, right? And so emission being that this is the radiation that the body itself is, you know, we can call it producing, okay? And that was the only radiation that left the body, because whenever other radiation came in, right? What we assume is that other radiation was just kind of perfectly absorbed by the material, okay? But now we're considering reflection. And so what that means is that when radiation comes in, some of it can actually bounce off, right? Okay. And this is important because now what we can say is that the radiation, if we just look at the body just by itself, right? All the radiation that comes off it is a combination of both the radiation that the object itself is naturally emitting, but also the radiation that it reflects as well. Okay? Okay. And so to account for this, we're going to define a new term. So that term is called radiosity. Okay. I don't know how this happened, but the symbol for radiosity is J, which I'm not complaining about because my name starts with J. But and so radiosity is exactly this. So radiosity is defined as all of the radiation that comes off of a surface. Okay, and most of the time that's going to be due to emission and reflection. Right? And so what we say is that J is equal to E. Right, so E is the emitted radiation. Okay. And to that, we're going to add the reflection, right? And so the reflection is going to be the product of rho times G. Okay. So E, let me just define all these. E is the emitted radiation. G here, this is the irradiation. Remember, irradiation, the way that we define that, that's the total amount of radiation that comes into the surface. Okay. And rho here, this is our reflectivity. Okay. And so reflectivity is a coefficient, and so it's between 0 and 1 as well. And that reflects the percentage of radiation that actually reflects off the surface. Okay. Okay. All right, so I introduced this concept of radiosity because it's going to be useful for us in our calculations. Okay, because if we compare, this situation compared to the example that we led with in this class, we can see clearly that this phenomenon of reflection is going to affect our radiation exchange calculations. Okay? Okay. We'll go over that in a second. Right. But before I do that, are there any questions on just the concept of radiosity? Yeah. Yeah, it's rho. Yeah, so same symbol as density. Yeah. Yeah, the Greek alphabet was not big enough, and so they have to reuse a lot of symbols. Yeah.
How do you gauge how much rho is activity?
Yeah, so that's going to be a property of the surface as well. And so, I think it's the easiest to think of like the extreme cases. So something like a mirror will probably have reflectivity of like 1 because that reflects basically all the light that comes at it. But then something like sandpaper or something that's not reflective at all. These tables are a little bit shiny, so they probably have some reflectivity. Those will have like reflectivity of 0. Yeah. Yeah. So it's a property of the surface finish, basically. It's both. And so, I mean, certain materials will have higher propensity to reflect than others, but you can affect it a lot by the surface finish as well. All right. And so, I think, after thinking about this for a while, when I was first preparing these lecture notes, I think the easiest way to think of these concepts is to think of them in terms of thermal circuits. And so, I know probably you guys are probably sick of thermal circuits in this class, but it kind of lends itself really nicely to this. Okay? And so let's connect these concepts. So concepts of radiation exchange as well as gray body radiation to resistances. Okay? And what you'll see is that this idea of radiosity and reflection, it connects to a very kind of key concept in thermal resistances that actually, admittedly, we haven't really done much with in this class, but here it helps a lot. Okay. This also, maybe a little bit decent review for the final as well. Because I'm going to bring us back all the way to kind of the first week of the class, right? And so let's look at conduction through a flat wall, okay? All right, so here is our wall, right? And so it's a solid block of material. Okay. It has some thermal conductivity K. The thickness of the wall or the length of the wall is L. Okay. And what we can say is that the cross-sectional area of the wall is A, right? And if we have a temperature difference here, so let's say that the left side is held at T1, the right side is held at T2, right? What we can say is that we can form a thermal circuit here. And so if we say that we have a thermal temperature node T1 here, okay? And if we say that, we'll assume that T1 is greater than T2, okay? What we can say is that these two temperatures are going to be separated by a resistance, okay? And this resistance is given by L divided by Ka. And so if we want to compute the heat transfer in this situation, we can say that this is going to be equal to the difference in the nodal temperatures, T1 minus T2, okay, divided by the thermal resistance. And so we divide it by L divided by Ka. Okay. And so there's this idea that if you have two different temperatures, right, and they're separated by a solid surface or solid material, then you can compute its heat transfer using this idea of a thermal circuit, right? And so any differences of temperature are usually going to be due to some kind of resistance in between. Okay. All right, so let me draw kind of an analogous situation with radiation. Okay. So actually, this kind of brings us back to our last example as well. And so in radiation, let's say that we have two surfaces here, okay? We'll say that there's a vacuum in between them. And so, the only way that they can transfer heat is radiation, okay? Right, we'll say that they have certain temperatures, T1, T2. They might be separated by a certain length. And we'll say they have a certain cross-sectional area as well. Right, what we just learned from our previous example was that the Q exchange between these two is F12 A1 sigma T1 to the fourth minus T2 to the fourth. Okay. But what if I did this? And so what if I did Q exchange, or I'll just shorten it to Q for now, is equal to T1 to the fourth minus T2 to the fourth, okay? And everything else, well, let me put sigma up here too. Right, everything else we're just going to go into the denominator. So we have 1 over F12 A1. Okay? If we compare our conduction formula with our radiation formula, right? They look pretty similar, right? And so on top, we have a difference in temperature. On radiation, of course, we have to raise the temperature to the fourth. But on the bottom, we have some properties, right? And what's important is that the properties on the bottom, those are properties of the, they're not really thermal properties, but they're properties of geometry, they're properties of the material, things like that. And so we can draw a very similar thermal circuit here. Okay. T1 and T2, right? And then separating them is not going to be a conduction resistance, but it's going to be what we think of as a radiation resistance. Okay? Well, I guess it'd be more accurate to say that, instead of T1, T2, we can say that this is equal to sigma T1 to the fourth and sigma T2 to the fourth. Okay. And so it's a little bit modified, but we can kind of form the same idea here. Okay. Questions on this? Yeah.
Is it a cross-section area or is it a surface area?
It's a surface area. Yeah. Yeah. Remember, radiation is coming off the exterior surface, and so it's going to be surface area. And so when you look at it like this, the concepts are very similar, right? And maybe this shouldn't be too surprising, right? Because the whole idea with heat transfer is that heat is always going to go from higher temperature to low temperature, right? You remember on the very first day of class, I said, everything you need to know about this class, that heat just goes from higher temperature to low temperature, and that's been kind of true this entire time. Is there another question as well, or no? Okay. Of course, we can draw a very simple circuit like this when there's only two surfaces, but things can get out of hand pretty quickly when you have more than two surfaces, right? And so let's look, for example, in our previous example. Okay. And so here, I'm not going to do any calculations, but I'm going to draw the radiation thermal circuit for basically the example we did at the beginning. And so in that example, we had 3 walls here. Okay. So this is surface 1, surface 2, surface 3. Okay, and we call that surface infinity. Okay, so we can use the concept of a thermal resistance in thermal circuits to draw one for this. Okay. The problem is, and the thing that's going to be complicated is that as long as one surface can see another surface, it can exchange heat from radiation, okay? And so we saw that in the last example, right? And so in the last example, what we saw is that surface 1 is radiating heat, not to just one other surface, but it's going to give it to surface 2, to surface 3, and to surface infinity, okay? And so that means, let me go ahead and draw, whoa. Okay. So let me draw nodes here to represent our 4 different surfaces. And so this will be node 1, and so this is sigma T1 to the 4th. This will be sigma T infinity to the 4th. This will be sigma T2 to the 4th, and sigma T3 to the 4th. Okay. All right, so from our last example, we know that surface 1 is going to exchange heat with surface 2, right? And so we're going to put a resistor there. And so this resistance here is going to be 1. This will be 1 divided by A1, F12, right? It's going to be exchanging heat with surface infinity here. Okay. And so this is going to be 1 divided by A1, F1 infinity. Okay. But it's also going to be exchanging heat with surface 3 as well. Right? So we have 1 divided by A1, F1, 3. Okay. But surface 1 is not the only surface that gets to radiate here, right? All 4 of our surfaces here can radiate. And so that means between any 2 nodes here, right? All our surfaces here can see each other, right? And so, surface 3 can see 1, 2, and infinity. Surface 2 can see 1, 3, and infinity. Surface infinity can see 1, 2, and 3, right? And so between all of the nodes in the system, we're going to have resistances. And so that means they're going to connect surface 2 and 3. Okay, so this is going to be 1 divided by A2, F2, 3. Okay. 3 and infinity are going to connect. And so this is going to be 1 divided by A3, F3 infinity. Okay. And we're going to go across from up to down too, right? And so surface 2 and surface infinity are going to connect as well, right? And so if we connect these two, right, that's going to be 1 divided by A2, F2 infinity. Okay. I apologize, it's a little bit messy just because my hand is sweaty as hell right now, and so it doesn't slide that easily. And this freaking glove that I bought from Amazon is not helping at all. And so, you know, it makes it hard to kind of draw big pictures like this. But, you know, you can see we have a pretty complicated network of resistances here, right? And so it's not just, heat's not just flowing in one direction. Heat can go in any direction, right? And so whenever you see a resistor here, that's a viable path for heat to move in this system, okay? Okay. Right. And of course, you know, with all these resistances, I mean, there's a lot of view factors to compute as well. And so, you know, there's a lot to do here. Right? And so these radiation systems, you know, very quickly get out of hand. So if you have kind of, you know, even just 4 surfaces, and so you would look at this geometry, you think, you know, that's not so bad. There's only 4 surfaces. But even with 4 surfaces here, you know, there's still a lot going on. So once you start getting 5 surfaces, 6 surfaces, 7, you know, this really gets out of hand. Okay, and so that's you know, another reason why radiation is it's pretty complicated. Okay. All right, any questions on this? Yeah.
Would it matter if we said if we're going like moving factor from 3 to 3?
Yeah, no, it doesn't matter. And so with the reciprocal rule, you can use either one. And so any of these, right? And so instead of A1, F12, you can do A2, F21 as well. And by reciprocal rule, that's going to give you the same thing. And so usually the best way to do this is to kind of like approach it like we did the last example, like focus on just one surface. Because if you can start to fill in, you know, all of the F11, F12, F13, then you can usually find the others through completeness. And so, so you have options here, and that's kind of what also makes these problems more difficult too. You have to have a little bit of a good strategy going in terms of which view factors are going to compute. Because it is possible, you know, in some of these problems, it is possible to use the tables for everything. You know, but with the tables and with how complicated those equations can be, you know, it can get out of hand pretty quickly. And so you want to be a little bit strategic on how you compute the view factors for sure. Yeah. Okay. All right. So that's great, right? But we kind of got off track a little bit, right? And so, you know, I kind of opened up this section talking about this idea of radiosity, but we haven't brought it up yet, right? And so let's kind of merge these two concepts, right? I brought up thermal resistances precisely so that we can talk about radiosity. Okay. And so let me bring up my our conduction example from before. Right? Okay. And so our conduction example, right? We had a block of solid material here. Okay. We had T1, T2. Okay. And so what we says that, you know, if we have just one thing like this, right, then we have just one resistance separating the two, right? And what we said for this is that this conduction resistance right? This is equal to L over Ka, right? And that would be the only resistance separating the two temperatures. But if you remember, when we first started talking about thermal resistances, we said that there might be some other resistances in this kind of situation as well, right? Because if you have kind of a nice clean, if you have kind of nice clean surfaces here, and there's no roughness or anything, then you would have this, right? But what can happen sometimes is that when a temperature interacts with a body, right, there might be some gunk that's on these surfaces, right? Not that much gunk. Oh my God. Okay. And so what these gunks do is that they add what we call contact resistance, right? Okay. And so these contact resistances are usually, they're usually some kind of surface effect. And so they're usually maybe some kind of rust or maybe some kind of mold or gunk that forms on the surface, right? And so these have an influence on the heat transfer, although usually they're too thin or they're too, they're a little bit too minuscule to kind of to characterize it in any other way. Okay. And so in these situations, what we say is that the total heat transfer, right? If we draw our circuit here, and so if we draw our node T1, and we draw our other node T2, right? Of course, we're going to have our conduction resistance, right? Okay. But we can also have additional resistances here due to the contacts, right? And so what we can say is that we can have a resistance on this side, as well as a resistance on that side. Okay. And these will be our contact resistances. Okay. Right, so let me just kind of drop the definition for contact resistance again. And so this will be some surface property or some surface gunk. Okay. Okay. And so the surface roughness is just any kind of gunk or surface roughness that can impede heat transfer. Okay. So we did a little bit of it. I know we did one homework problem where I said we can add some spray paint, and the spray paint will be some extra resistance. Okay. But we can take the exact same concept and apply it to radiation as well. Okay. And so let's see how we can apply this radiation onto gray bodies. Okay. All right, so let me bring up our example from before, right? And so we had two parallel surfaces here. Okay, so we're just going to focus on two. Right, where this one will be T1, this one will be T2. Okay. Maybe they have some kind of view factor between them. Okay, so we're going to do F12 or F21. And so what we saw before is that if we have our thermal circuit here, and so we have sigma T1 to the fourth, is sigma T2 to the fourth. Okay. We know that there's going to be a factor that impedes the radiation that has to do with their view factors, right? And so this is going to be 1 divided by A1, F12, okay? But what we've also been talking about today is that, these surfaces may not be perfect. And actually, actually literally all surfaces are not perfect, right? And so black body radiation, in theory, it might exist, but we haven't been able to recreate it in the real world. Okay. And so kind of the radiation equivalent of surface gunk or surface features is when our emissivity is less than 1. Right? So we might say that emissivity here less than 1, emissivity here less than 1. Okay. And so what we say is that because of that emissivity, we're going to have an additional resistance here. So we'll call that R epsilon just for now. So we'll call it R epsilon 1, R epsilon 2. Let me label them differently, just to be as generic as possible. So these two can be different surfaces. Okay. Okay. And so in a very similar way, the fact that any surface properties can impede conduction heat transfer, having emissivity less than 1 can also do the same thing. Okay. Okay. And so how do we define these? And so these emissivity resistances have a formula. Okay. And so I'm just going to give it to you. We're not going to derive it. Okay, so what we can say that our emissivity 1 is going to be 1 minus emissivity. I drew a xi for a second. Okay. Divided by epsilon 1 times A1. Okay. And similarly for R epsilon 2 is equal to 1 minus epsilon 2 divided by epsilon 2 A2. And so kind of in summary, right? So having emissivity less than 1 is going to add some additional thermal resistance to our radiation exchange. Okay. All right. Let me pause here for a second. So are there any questions on this? Okay. Let me bring in one other concept, just because we haven't brought this guy in yet. Let's bring in the concept of radiosities. Okay. And so I'm going to draw some additional nodes here, okay, in our circuit. Notice the locations of these nodes. And so these locations are going to be always after a emissivity resistance. Okay. And I'm going to mark those nodes J1, J2. Okay. So J1 and J2, right? As a reminder, these are the radiosities for surface 1 and surface 2. And remember what they represent, right? So remember, radiosities represent the combination of both the amount of radiation that's emitted as well as the radiation that's reflected off of these surfaces, okay? All right. And so these are important because, when we think of nodes, right? The nodes in our thermal circuits always play a key role. And so the nodes play the role of, allowing us to compute heat transfer, right? It's not time yet, right? We got 5 more minutes. Oh, I see. Okay. right? And so very similar to the way that we use temperature nodes in our normal thermal circuits, right? And so, if we drew nodes right here, right? And so we said this is maybe TA and TB, okay? Right? And so those will be the temperatures kind of right outside the contacts, right? So right outside the gunk, right? We can compute the heat transfer as TA minus TB divided by our conduction, right? So that's how we use nodal. That's how we use nodal values before. Okay. With radiation, it's a little bit different, because we don't have temperature straight up at the nodes. We actually have what's called its emissive power. Okay. They're excited to take a test, huh? Okay, and so we can use the radiosities in the same way. And so what we can say is that if we don't want to consider the outsides of the circuits, we can use J1 and J2, right? And so what we can say is that Q12, okay? Of course, Q12 from surface 1 to surface 2 is going to be sigma T1 to the 4th minus T2 to the 4th, okay? All divided by the sum of all the resistances but we can also compute Q12 based on the radiosities, right? Okay, and so if we use J1, J2 here, we can say that Q12 is equal to J1 minus J2. Okay, and the only resistance in between J1, J2 is the view factor resistance, and so we have 1 divided by A1 F1 2. Okay, and so both these formulas are equivalent, because we use different nodal values. Okay, I'm just looking ahead a little bit. Right, and so we're going to stop here for mostly today, okay? Because what I have left is just basically 2 examples to show how this is going, okay? But I will say that we are going to, the way we're going to set up these problems, what we're mostly interested in solving for are these radiosities in general, okay? Because if we say that if we know the radiosities, then we can compute the heat transfer between any 2 surfaces. Okay. The unfortunate thing with these types of problems is that for a problem like this, it's not that bad. Right? But the way that we set up our equations, we're going to have to solve a linear system of equations for J1, J2, right? And so I want to kind of warn you right now. Okay. And so it's kind of unfortunate how this kind of is structured, just because we haven't done linear algebra in this class yet, and then all of a sudden we have to do it in kind of a very intense way for these kinds of last problems. And these really are kind of the last types of problems that we're going to go over in this class. Okay? All right, so I want to warn you just kind of up front, because we're going to be doing some linear algebra next time as well. All right, any final questions before we wrap it up for today? Okay, all right, and so next on Monday we'll pick this up again. We're gonna conclude with just 2 final examples, and then that'll be it. That's EGME 407 for you guys. All right, so thank you guys for tuning in today. Hope you guys enjoy the rest of your weekend. You should be able to get a pretty good start on the homework now, and I'll see you guys next week. Next Friday. Yeah. Yeah. If you haven't picked up your exam yet, you can come pick it up. If you're on Zoom, you can come to my office anytime to pick up the exam as well.
So on this problem.
Yep.
No.
Yes, yeah, the length here is 0.1. These ones here are 0.1.
So when we're running for infinity, why are we using 0.5?
We should have used 0.1.
We use 0.5.
Oh, so this is the area of the emitting surface. This is A1. And so A1 is always going to be the surface of the area of the surface of the emitting surface.
So what if it's 0.5 times.
Exactly.
And then also, I think you missed this.
Yeah, I looked at that, I think that's a typo. This should be cute.
Yeah.
I'm not sure.
I got 2,000.
Okay, oh, she put it in the calc. Okay, maybe it wasn't a typo. Because it looked really small, because this calculator is huge.
No, all of them we got about 1,000. That's what I got in my calculator.
Okay,
But I
okay,
was
if that's what
just,
you got.
I
then-
checked with the two numbers, so this should be.
Okay.
Maybe it's one. Is that why it's one?
Yeah, meeting one is one.
This one was, I thought it would be.
I
Okay.
still.
That's surprising.
I tried to flip it. I tried to change it. I tried to change it.
Ooh, so I teach a class, but I am free after that. You can be at 5:30. Yeah. Okay, let's do Tuesday 5:30.
Yeah, because the next thing else, we have to 12, but I should have specified Monday, Wednesday, Friday.
Oh, okay. Okay, yeah, no problem. Yeah, you can do Tuesday 5:30. We'll do the same Zoom link. I am. Oh, I can reset that. Everyone is gone. I just forgot to.